So review for final, Calc 1. We'll start with Chapter 1. 1.4, just to understand the tangent problem, which is the essential problem in differential calculus. That is to find the equation of a tangent line at a given point to a given curve. 1.5, limits of a function. So we had several techniques here. We had direct substitution. For example, limit x goes to 0, cosine of x plus sine x. You always try direct substitution first, which means substitute x with 0. And if this is possible to calculate, then that's the limit. If it's not possible, for example, you have to divide by 0, which is not defined, you have to do some algebraic techniques, which we're going to see later. So right now we can substitute, and we have 0 plus sine of 0. Sine of 0 is 0, so cosine of 0 is 1. Example 2, limit x squared minus 9 over x squared plus 2x minus 3, x goes to negative 3. If you try direct substitution now, you're going to have 0 over 0, which is undefined. So we need to do something, which is, in this case, factoring. So we factor the top, we factor the bottom, and fortunately, we are going to cancel x plus 3, which is the bad factor that causes that 0 over 0. So we're ending up with limit x minus 3 over x minus 1, where you can do direct substitution, and you have negative 6 over negative 4, which is 3 over 2. Then we talked about one-sided limits. So those are limits from the left or from the right. Example 3. Let's look at this piecewise function, which is equal to 0 if t is negative and 1 if t is positive. You can sketch the graph. So here is 1, and here's the other side. Is that right? If 0, oh, that's not it. 1, this is correct, but then this other part is not. So this is 1 here, but it's 0, that means it's this part. All right, so it's a piecewise function. And what can we say about the limit of this function when t approaches 0? Well, from the right, that limit is 1. From the left is 0. So if the right hand, the left hand limit are different, we can say this limit does not exist. Why? Right hand limit is different from the left hand limit. Example 4, limit of 4 minus v over absolute value of 4 minus v. V goes to, approaches 4 from the right. So now you have to be careful. You cannot cancel. You have absolute value. So every time you have absolute value, you have to consider the piecewise function. What is 4 minus v equal to? Well, it's equal to 4 minus v or negative 4 minus v, depending what v is. So it would be positive if 4 minus v is positive, which is v less than 4, and it's negative if v is greater than 4. All right, and we can put the equal sign anywhere, doesn't matter. So in our case, v approaching 4 from the right, that means it's greater than 4. So in this case, so we're going to use that equation. So we're going to have a limit of 4 minus v, and on the bottom, negative 4 minus v. V approaches 4 from the right, so now we cancel. And what's left is just negative 1. All right, example 7, actually example 5. we're going to have a picture here of a function that has problems. It has a jump, it has a hole, we'll call it g of x, and the problems are at 2, so this is 2 here, and then again, let's call this point 4. All right, so we're going to look at several limits here. This point, let's call that 2, and all right, this will be 1. Let's look at the limit of this function when x approaches 2 from the left. So from the left, the y value is approaching 2. What about from the right? 2 from the right, it's approaching 1. So these two are different. Therefore, we can say that the limit when x approaches 2 does not exist. We have a jump. All right, let's look at the limit of our function when x approaches 4 from the left. So from the left, this is between 1 and 2, I'm going to say 1.5. What about from the right? X is a little bit bigger than 4. From the right, oh, it's approaching the same y value. So these two limits are equal, therefore, the limit when x approaches 4 will be the same, 1.5. All right, now we can redefine this function. We can say that the value of the function at 4 is 1. So we can say f of 4 is 1. That's how it's defined it. So we saw that the limit exists. We had a limit at 4, even though the function was defined at 4 at a different point, or not even defined. It didn't matter. All right, so continuing with infinite limits, we're still in 1.5. Infinite limits. Example, find the limit of 1 over x squared if it exists. We know it exists if the left side and the right side are equal. Limits are equal. So x is approaching 0 here. We can look at the graph, familiar function. What's happening at 0? Let's look at the left-hand limit first. X approaches 0 from the left, and the y value is approaching infinity. What about when x is approaching 0 from the right? Again, is infinity. So these two are the same, even though they're not numbers, they're infinity. So the limit of this function when x approaches 0 is equal to infinity. So it doesn't exist if they're different, but if they're the same, we say what it is. It's infinity. So we have a connection between limit at infinity and vertical asymptotes. So we have vertical asymptote in this case, vertical asymptote, which is the y-axis, or x equals 0. So here's the connection here. We are approaching 0, and we have vertical asymptote at x equals 0. So that's not an accident. We find vertical asymptotes if any one of those limits is positive or negative infinity when x approaches a from the right or from the left, or maybe I can just write this from the left, from the right, or from both. So if, I'm going to say here, let's do this, erase that. I'm going to say if any one of those limits is infinity, positive or negative, then we have vertical asymptote at that point, x equals a. All right, example, prove that the limit absolute value of x over x when x approaches 0 does not exist. Okay, so approach this the same way. We can look at the graph of this function. If x is positive, here's our function. If x is positive, then we have 1, right? X will cancel, and it's -1 if x is negative. So the graph looks like this, just like our piecewise function earlier. So the limit from the right is different from the limit from the left. Okay, so we can say the limit of our function from the left is -1. The limit from the right is 1. These two are different. Therefore, the limit when x approaches 0 does not exist. All right, so we've seen if you have a jump, then the limit does not exist. If you just have a hole, the limit exists. So another thing we study here, it's called the squeeze theorem. The squeeze theorem, or sometimes we call it the sandwich theorem or the pinching theorem. And it goes like this. If we have three functions such that g is between the other two, and doesn't have to be everywhere, but when x is near a. And if we also have that the limit of f is equal to the limit of h when x approaches a, then the limit of g, the middle function that's squished between the other two, that limit is also L. So here's the picture. So we have a function h, we have a function, so this is h is the biggest one, f is the smallest one, and the one in the middle, g, could be anywhere, but it's between them in the neighborhood of a. So here's a, and this is over here, this is L. So you can see that the function g has nowhere to go, but has to go between h and f and have the same limit L. So we use that theorem whenever we have to find limits in a non-traditional way. So here's an example. Find the limit of x squared sine 1 over x when x goes to 0. So no factoring, nothing can help us here. We just have to compare a function with two other functions. So we're starting with the fact, the sine of a function, I'm going to say sine of t, so we don't have the same x. The sine is between -1 and 1. That's the range of sine. Now, if I, instead of t, I put 1 over x, that's still true. And now I'm going to multiply both sides by x squared, which is positive. So the signs remain -x squared less or equal to x squared sine 1 over x less or equal than x squared. So here are my three functions. So this is f, the smallest one, g is the middle, and h is the biggest one. So I'm going to let x goes to 0. So if x goes to 0, x squared goes to 0, and so does -x squared. Then the middle function has nowhere else to go, but goes to 0. So we can say here by the squeeze theorem, the limit of our middle function when x goes to 0 is 0. Another fact here, or a formula that we use a lot, we haven't proved it, but we can prove it in Calc 2 a lot easier with L'Hopital's rule. But if theta goes to 0, sine of theta over theta, even though it looks like 0 over 0, is 1. So very, very important formula. Add it to your formula list. That was all 1.5. 1.6, we had limit laws. They're very self-explanatory. Limit of a sum of the limits, and so on. So I'm gonna make a note here, no 1.7 for the final. That was the epsilon delta definition. And we're gonna go to 1.8, continuity. Continuity. So we need to understand the definition of continuous function at a point. We say f is continuous at a point A if three things. Number one, f of A is defined, so no holes. Number two, the limit of f of x when x approaches A exists, so no jumps. And three, these two are equal to each other. In other words, the limit of f of x when x approaches A, it's exactly f of A. So not continuous function means it has a break or it has a hole graphically, but we don't prove things by saying break or a hole. We use that definition. So very important theorem that says the polynomial, rational, root or radical, trig functions are continuous wherever they're defined, or I'm going to say on their domain. Now, the polynomial functions are defined everywhere, so they are continuous everywhere. The rational root trigs have a domains on their domain. They are continuous. Okay, there is another theorem here, the intermediate value theorem. Okay, I'm going to ask you to look it over and review it. Just make sure you understand it. And I'm going to go to chapter 2. 2.1, derivatives and the rate of change. So we had two definitions here for the slope. So the slope m can be written, it's rise over run, but we define it as a limit, f of x minus f of a over x minus a when x approaches a. Or definition 2, well, we use h. Instead, h goes to 0, and it's on the denominator, f of a plus h minus f of a. So we use those definitions about whenever we have to find the slope. Okay, derivative. Derivative of a function f at a point A. So derivative is derived from f. So that's actually the slope. And I'm going to use, we use here the second definition. So this is the derivative and this is the notation. And h goes to 0 here. So equation of the tangent line. The equation of the tangent line, as we know it, is the point slope form. But we're going to write this form in a calc language. Keep the y, y1, that is f of a, m is our derivative. Keep the x, x1 is our point A. So this is the equation of the tangent line. Example, find the equation of the tangent line. Find the equation of the tangent line 2y equals x squared minus 8x plus 9 at the point 3, negative 6. So we have a parabola, and we need to find the equation of the tangent line. Now we're going to use a formula that we'll learn later on to save time, but if you can use the definition to find the slope. So the slope, or shall I write the derivative as a function? I'm going a little bit ahead here and using our knowledge for finding a derivative, but it's 2x minus 8. So if you substitute x with 3, because that's the point that's given, 2 times 3 minus 8 equals negative 2. So the slope is negative 2. The point is 3, negative 6. Just write down point slope form. Y plus 6 equals negative 2x minus 3. Y equals negative 2x. That's it, because the 6 will cancel. So this is the equation of the tangent line. 2.2, derivative as a function. So the derivative as a function, we use the same formula as before, but instead of a, we're going to use x because we let a vary. So the same formula as here, it's the limit of f of x plus h. The same formula, instead of a, we put x minus f of x over h goes to 0. So example, if f of x is equal to x to the third minus x, find f prime of x. Derivative is a function. So answer, you know the quick answer from the formulas, but if you use the definition, it's going to take a little longer, 3x minus 1. 2.3, differentiable functions. Differentiable functions. So we need to know what it means for a function to be differentiable. We say f is differentiable at some point a if f prime at a exists. So it's very simple. F is differentiable if f prime, that was the limit, exists. F is differentiable on an interval ab or a to infinity or the whole real number line if f is differentiable at every point on that interval. So graphically, continuous function means no holes, no jumps. Differentiable means it has to be continuous, but even more. There is more requirement here than what we had for continuous. So for example, the absolute value of x, this function or the v function looks like this. It's continuous everywhere, but guess what? It's not differentiable in this point 0. It's continuous, but not differentiable. And we can prove that. I'm going to write this down. So absolute value of x is not differentiable at x equals 0. It's differentiable everywhere, but not there. So graphically, and you can easily prove it, graphically, to be differentiable means no sharp corners. So no holes, no jumps, but no sharp corners. So sharp corners like this one, it means the function is not differentiable. All right, also another way for a function to fail to be differentiable is if it has somehow vertical asymptote. So at that point a, f is not differentiable at a because it has a vertical tangent. So the slope doesn't exist, the derivative doesn't exist. All right, then we talked about higher derivatives. That means second or third derivative. So the derivative of the first derivative is the second derivative. And so all rules apply. 2.3 is probably your most favorite lesson because here we learn the basic differentiation formulas. Let's start with the constant. Derivative of a constant is 0. Never forget that. The most famous formula in calculus, the power rule. The derivative of something to a power is n goes on the front, x to the n minus 1. Okay, so this works for every n except -1. So n is integer. N is integer. Actually, it could be for every n. It works for rational and irrational. All right, product rule. F prime g plus f g prime. Quotient rule. It's a little longer here. And we mentioned something briefly about a normal line. So normal line is the line perpendicular to the tangent line. So if two lines are perpendicular, then the slopes opposite reciprocal. Here's a function f, here's a point P, here is a tangent. So the normal line is perpendicular. This is N. And we know perpendicular lines have opposite reciprocal slopes. 2.4, more formulas. Derivative of trig functions. Derivatives of trig functions. So derivative of sine is cosine. Derivative of the cosine is negative sine. Derivative of the tangent is secant squared. Derivative of the cotangent, negative cosecant squared. And we had more with the, you can dig those for the secant and the cosecant. Here's a trig identity. They're very important. Sine squared plus cosine squared is 1, but also 1 plus tangent squared, or tangent squared plus 1 is secant squared. So we use that a lot. 2.5, we introduce the chain rule. That's when we have composite functions, not just simple functions. 2.6, implicit differentiation. And that is when you cannot solve for y, or it's difficult to solve for y, you can still find the derivative. So we're going to have some examples here. First, the chain rule. If I have y equals x squared plus x to the third, all that to the fourth, how can you find the derivative? Well, look for the outside function. It's the power function. So we're going to use the power rule. 4 goes on the front, x squared plus x to the third to a power 3 times, and here's the chain rule, the derivative of the base. Okay, so 4, we copy this, and the derivative of x squared plus x to the third is 2x plus 3x squared. Okay, I'm going to factor things out. I mean, you can leave it like this, but you can factor from here x squared to the third power is x to the 6th, and from here x, so you can do x to the 7th actually, x plus 1 to the third, 2 plus 3x. So this is just simplifying it. Another example with the chain rule now. Y equals sine of tangent of 1 plus x to the third. Y prime. The outside function is sine, derivative sine is cosine of all that. But then we have to multiply by the derivative of the input for sine, which is tangent of 1 plus x to the third, which in itself is a composite function. Okay, so the derivative of the tangent, we know it's secant squared of all that, times the derivative of the input for the tangent. So it's getting long here, but one more step. Okay, so the derivative of a radical function that's power 1/2. 1/2 goes on the front, 1 plus x to the third to a power, 1/2 minus 1 will be negative 1/2. And then I'm going to multiply by the derivative 1 plus x to the third, which is 3x squared. So finally, we can write everything as one expression. I'm going to write here one fraction, 3x squared, and on the bottom, I'm going to use a square root instead of power. And here you go. Another example. Find equation of the tangent line. and equates the tangent line to the curve at pi over 6, 1, and the equation is 2x plus 1. Okay. I think we're missing something here. All right, I'm gonna delete this example. I think it's missing. It can be aligned. This is probably a different curve. So let's skip this example. Going to 2.8, related rates. So quick example here, if I have formula for volume of a sphere, 4/3 pi r to the third, and if I implicitly differentiate in terms of t, so dv dt is equal to 4/3, and then pi stays 3r squared dr dt. So here are the two rates, dv dt and dr dt. One of them will be given to you, you have to solve for the other. 2.9, you can look at your tests and do an example from your test on chapter 2. Linear approximation. Linear approximation. Okay, so we use this method whenever the equation of a graph is very complicated. So we use a line instead to approximate. So the equation of the tangent line, to f of x at point A is y equals f of a plus f prime a x minus a. That's the point slope form basically. So we're using that equation to approximate the function, whether it's square root or sine, something complicated. We're using this tangent line equation to approximate a function. But it's very important to know that this is true when x is near a. So if x is far away from a, you have to pick another point. Chapter 3. 3.1, maximum and minimum values. We had several theorems here, but the extreme value theorem was important. Extreme value theorem. It basically says that if f is continuous, on closed interval, here it is, closed interval, then f has an absolute maximum and absolute minimum value at some point, at some points C and D in the interval. So you have both absolute maximum and absolute minimum. Then we introduce an important number called critical number. We can have examples on those. Critical number, call it C. So C is critical number if f prime of C is 0 or f prime of C does not exist. And then we had a method called closed interval method for finding absolute minimum and maximum. So I'm going to have an example with this method. Example, find the absolute minimum and maximum of f of x, polynomial quadratic, and the interval from 0 to 3. So you need to check, continuous. Is it continuous? Yes, all the time, everywhere, polynomial is continuous. Do we have a closed interval? Yes. So the methods works like this. First, you find your critical numbers. To find the critical numbers, you have to find f prime. So 6x minus 12, set it equal to 0, and x equals 2 is our critical number. Because this f prime exists everywhere, there is no other critical number. So here's the interval from 0 to 3. Actually, we don't need to sketch it. We just have to calculate the value of the function of the critical number and at the endpoints. And the biggest of those is the absolute max. So we're evaluating f, okay? So f of 0, that's easy, that's 5. F of 2, you can plug in and see -7. And f of 3, let me do this, 3 times 3 squared minus 12 times 3 plus 5 equals 27 minus 36 plus 5. So it looks like -4. So the biggest number is this. So that's the absolute maximum. And the smallest number is -7. It's the absolute minimum. We ignore the other one. All right, 3.2, we had two important theorems. Rolle's theorem and mean value theorem. So Rolle's theorem first. Okay, Rolle's theorem. It had three conditions. Number one, f, I'm going to say if, number one, f is continuous on the closed interval. Number two, f is differentiable on the open interval. Number three, f of a is equal to f of b. That means both ends of the graph are on the same level. Then there exist some number c in the interval such that f prime of c is 0. I'm going to illustrate this with a picture. So here is our graph. Both ends, both levels at a and b have to be equal. So we see this f of a, f of a is equal to f of b. All right, so where's that point C where the tangent is horizontal? It's right here, right in the middle. Okay, so that's the Rolle's theorem. And then the mean value theorem starts very similar. Probably should spell it out. Mean value theorem, MVT. So if, number one, f is continuous. Number two, f is differentiable. So far everything's the same. Then, but no third condition, then there exists some number c in the interval from a to b such that f prime of c is equal to the slope of the line that's connecting the endpoints. So here's a picture. We have a graph, but both ends are not on the same level. Okay, so this is f of b and this is f of a. So when you connect both ends, like this point and this point, you get this secant line. We can call it AB. And so our point C is somewhere here. Here's our point C. And as you can see, the tangent of that point C is the same as the blue line. They're parallel. Okay, so we also had an important consequence here, a corollary, that says that if f prime of x is equal to g prime of x, we have two functions and the derivative the same for every x in the interval then they're not necessarily the same functions, but they're in the same family. The difference between them is a constant. 3.3, derivatives and the shapes of graphs. Derivatives and the shapes of graph. So what does the derivative can tell us about the graph of f? What does f prime say about the graph of f? Well, plenty. It can tell us increasing or decreasing, minimum or maximum. So we had here this so-called increasing, decreasing test. This is very important. Will be important later on in Calc 2. Increasing, decreasing test. It's very simple. It says that if f prime is positive on an interval I, then f is increasing on that interval I. Makes sense? You can draw a picture. F prime positive means the slopes are positive. That means they go up and to the right. And if f prime is negative, that means the slopes are going down on interval I, then f is decreasing on that interval I. Example, find intervals of increasing and decreasing. Find intervals of increasing and decreasing. F of x equals 2x to the third minus 3x squared minus 12x. So we need first derivative, first thing. 6x squared minus 6x minus 12. You want to set it equal to 0, find critical numbers, factor out 6, x squared minus x minus 2, and then factor. We can ignore the 6. How does that factor? X and x, 1 and 2 minus plus. Does that work? 1 minus 2, negative 1. Okay, so x equals negative 1 and x equals 2 are the critical numbers. So the easiest way to do is put them on the number line. This function is defined everywhere, so we don't have domain to worry about. So here's negative 1 and here's 2. All right, check the sign of f prime. So pick a number, random number, let's say from here, 5. If x is 5, and plug in f prime, you're going to get, let's see, 5 plus 1, positive. Then pick a number from negative 1 to 2, let's say 0. You're going to get negative, and here you're going to get positive. So the pluses means increasing. We can say f is increasing where the pluses are. That means from negative infinity to negative 1. Never do brackets on intervals, always open interval. And from 2 to infinity. And we can say f is decreasing from negative 1 to 2. Always open intervals. Then we had first derivative test. That tells us when you have minimum or maximum. So it starts with a continuous function, f continuous, at least on the interval. And c is a critical number, which we know what it is. Two cases. If f prime changes from positive to negative at c, then f has, from positive to negative means from increasing to decreasing. Then what do we have at c? F has a local maximum at c. You can see that from the graph. And b, if f prime changes from negative to positive at c, then f has a local minimum. Let's see. So you don't have to remember the rule. You actually have to kind of imagine what's happening, back to our example here, we are changing from positive to negative. So at that point, -1, we have a local max and a 2. So the function was increasing here, then decreasing, and then increasing again. So what do we have at 2? A local minimum. So one sign chart and you get increasing, decreasing, and your local minimum and maximum. All right, you can review the second derivative test. I'm going to go on and talk about the second derivative now. What does the second derivative say about the graph of f? Okay, so let's look at the picture. And here's a graph where the shape is upward. So we say this is concave upward. So in this case, the second derivative is positive on this interval, and concave downward, concave downward. If you continue the graph, it looks like a parabola opens down. Here, the second derivative on that interval is negative. We also had inflection point. Inflection point. So inflection point is when the concavity changes. Here, this is an inflection point. Point where the concavity changes. And it doesn't matter from concave upward to downward or the other way. So sketch the graphs here based on this information. I'm gonna go on with that example, look at your tests and review the examples there, as well as the second derivative. Let's go on to 3.4, limits at infinity. Horizontal asymptotes. So if the limit of f of x is L when x goes to positive or negative infinity, then y equals L is horizontal asymptote. Okay, then we talked about infinite limits at infinity. Example, what is the limit of x squared minus x when x goes to infinity? We talked about not subtracting or adding infinities. They're not numbers. But the strategy here is to factor out x. So if I factor out x, what I see is that this part goes to infinity. And I didn't factor this right here. It's x minus 1. So we see x goes to infinity. X minus 1 also goes to infinity. So basically I have infinity times infinity. So that is infinity. Another example about limits at infinity here and a strategy. For example, how do you find the limit of a rational function when x goes to infinity? 1 plus 2x minus x squared is on top, 1 minus x plus 2x squared. So if you substitute, you get infinity over infinity. Our strategy was to divide both numerator and denominator by the highest degree of the denominator. And that in this case is by x squared. So we have 1 over x squared. I'm going to divide each one individually. And cancel. So after you cancel, you're going to get negative 1/2. Is that right? Yep, negative 1/2. Because this part is going to go to 0, and so is this. And after you cancel will be this one and this one. Now, when you cancel this, that's going to be negative 1, and that's going to be 2. So important fact that we use here is that the limit of 1 over x to some power p positive, when x goes to infinity, p is positive. This limit is 0. So what happens if we don't have a denominator? One more example here. Limit of square root x squared plus 4x plus 1 minus x. X goes to infinity. Again, it could be infinity, it could be a number. So the strategy here is multiply, and divide. Multiply and divide by the conjugate, which is square root x squared plus 4x plus 1 plus x. All right, and the answer here, you should get 2. Answer 2. Surprisingly enough, that limit is not infinity, but a number. So a little bit left to finish chapter 3, 3.5, summary of curve sketching. Curve sketching. So find an example of a graph and practice sketching. 3.7, optimization problems. These are problems about minimum, maximizing, minimizing. Review some problems from your notes or from the test. 3.8, Newton's method. First and second approximation. So the Newton method is the following. We want to approximate solutions of some complicated equations. So here's our f of x, and we may know the equation, but it's very, very difficult to solve. This is the 0 or the solution r. We try to approximate r, but we can't find it exactly. So what we do, we start with x1, our first approximation, which is either given or you have to guess it, and then we do the tangent here, and where that tangent intersects the x-axis, that's our x2, second approximation. So we continue that process and we derive the formula that x2 is equal to x1 minus f of x1 over f prime x1, and so on. We actually have a formula for the nth approximation, which you can write from here. I'm going to say xn plus 1 is equal to nth minus f of xn over f prime of xn. And 3.9, antiderivatives. Antiderivatives, which is a preparation for our integral calculus. Again, review examples from your test or notes. With this, I'm going to finish part 1 of the review for final.